Exercise 1714 is asking you to predict the products for some Diels-Alder reactions. And so this is one of the most significant reactions in organic chemistry. It's definitely changed human history. People were able to synthesize antibiotics, some antibiotics like tetrodotoxin for the first time. They were able to synthesize cholesterol in the laboratory because of this reaction. So it's really worthwhile to take some time and really master this one. It could be useful in creating new medicines if you go into research or go into medicine in the future. So in order to predict the products, you would want to look at the diene, that's the molecule that has the two conjugated pi bonds, and draw a dot at the end of the conjugated system. So draw dots there. And then go to the dienophile. The dienophile is the one that has that one carbon-to-carbon double bond in it. Now there's other stuff here. So there's these usually have electron withdrawing groups. Remember in that last video that we made discussing the concept behind the Diels-Alder reaction, that it's the LUMO, the lowest unoccupied molecular orbital of this dienophile that's going to be involved in the reaction. So it's that orbital is the one that accepts extra electrons from the diene. And it's easier for this to accept extra electrons if the electron density in it is pulled away by these electron withdrawing groups. So you'll notice all the electronegative elements, and it's also withdrawing electrons through resonance. So that's why you'll notice all these weird, very electronegative, very resonant, very electronegative elements on the diene all the time with resonance. Those are stealing electron density away from the diene to make it really ready to accept some electron density from the highest occupied molecular orbital of the diene. So your first step is just to draw dots at the end of the conjugated system for the diene and at the end of the two carbons in the dienophile, in the double bond there. And then just draw a dotted line between them. Those are the two new bonds you're going to form, the two new sigma bonds you're going to form. Once you have those, move all of the pi bonds in the same direction. Now by direction, I mean here like clockwise or counterclockwise. So we can, let me just take these pi bonds, and I'm going to draw them in different colors. So say green, and then dark blue here, and then let's say purple on top. So this way we can track how they're moving. So these green pi electrons, I'm going to move those clockwise. They're going to form a sigma bond. The blue ones, I'm going to move those clockwise. They're going to form a pi bond in a different place. And the purple ones, I'm going to move those clockwise. They're going to form another sigma bond. So if you want, if it helps you, you can number the carbons. So we have 1, 2, 3, 4, 5, and 6. So we're going to draw a ring with 6 carbons. Oops. And if we were numbering it, we've got 1, 2, 3, 4, 5, and 6. So notice how the purple electrons are going to go from being between 1 and 2 to being between 1 and 6. So they're going to form this sigma bond here. Notice how the green electrons are going to go from being between 5 and 6 to being between 4 and 5. So they're going to form this other sigma bond here. And then those blue electrons are going to go from being between 3 and 4 to being between 2 and 3. Finally, you just want to add those electron withdrawing groups back on. Now notice in this double bond, those were cis, right? If you draw a dotted line down that double bond, both of these are to the right of that. So they're both on the same side of that dotted line, of the long end of the double bond, so they're cis. And so you want them to be cis in this ring. So either they'll both be going up or they'll both be going down. So we'd have that, and then O, M, E. The ME is just standing for a methyl group. And I'm drawing them both coming out at you, so both solid wedges, but they could just as easily both be dashed wedges. And so that would be the product for this Diels-Alder reaction. That's what you'd expect to get when you mix these two reactants together. So going through the same procedure for B, draw dots at the end of the diene, and draw dots at the end of the double bond in the dienophile. Connect those with dotted lines. Those are the two new sigma bonds you're going to form. I'll draw in the pi bonds, the pi electrons with different colors so we can follow them a little more easily. And then choose a direction, either clockwise or counterclockwise, and move all those pi electrons in that direction. Here I'm going to move them all clockwise. One bond over. If it helps you, you can number the carbons to keep track of where everything is. I'm just numbering the ones in the diene and the dienophile, because that's where you're forming the ring. So you've got that diene carbon skeleton, you have the dienophile carbon skeleton. If you were numbering them, it would look like this. And those purple electrons move from being between 1 and 2 to being between 1 and 6, so those form that sigma bond there. The green electrons move from being between 5 and 6 to being between 4 and 5, so those form that other sigma bond here. The blue electrons move from being between 3 and 4 to being between 1 and 2, so those form this new pi bond here. So that's our ring. And then we just have to add in those electron withdrawing groups. They're both cis, so if you draw a dotted line down the double bond of the dienophile, you'll see that both of these are carboxylic acids in disguise. So that COOH is really this in a condensed form. So that's the same thing as COOH. So those carboxylic acids are cis to the double bond, and so we'll just want to draw them in as cis. I did the last one as coming out at us. You could just as well do it going away. So you'd have this, and here I'll draw it out just so that you can see, just to reinforce that that group COOH is a carboxylic acid. And so that is the product for the Diels-Alder reaction that you'd get for those when you add that diene to that dienophile. All right, so with this one. Now, this one's a little tricky because they don't give you the molecule nicely lined up. So I would actually do that first. I would line up the molecule nicely. So just redraw them. And I'm going to have the double bond of the diene, this double bond here, aligned so that we can kind of see how it'll fit together in the ring. Now, notice that these two electron withdrawing groups are trans. If you draw a dotted line down the long end of the double bond, those groups are on opposite sides of that double bond, so they're trans. So you'll have one going in one direction and the other going in the other direction. Okay, well, at this point, it's the same procedure as last time. Draw the dots at the end of the conjugated pi system of the diene, draw the dots at the end of the dienophile, and then just connect those with double bonds, or with dotted lines. I'm going to draw in all of these pi electrons with different colors so we can just track them a little bit more easily. So then pick a direction, either clockwise or counterclockwise, and move all of those pi electrons in that direction. So here I'm going to move all of these clockwise, one bond over. If it helps you, you can number the carbons in the diene and the dienophile, so you can kind of keep track of everything. Here we've got 6 carbons. So we'll redraw that carbon skeleton of the diene and of the dienophile. And we can number those so we can always, it's easier to see whether we've drawn the right structure or not. So the green electrons are going to move from going between 5 and 6 to going between 4 and 5. So those form that sigma bond right there. The blue electrons are going to move from going between carbons 3 and 4 to between carbons 2 and 3. So they form that new pi bond there. The purple electrons are going to move from going between carbon 1 and 2 to going between carbon 1 and 6. So that's that new sigma bond there. Now for the branches, the electron withdrawing groups coming off of the dienophile, those are trans. So they're still going to be attached to carbons 5 and 6, but they're going to be trans on the ring. So if one is coming out at us, then the other has to be going away. So they're trans. Now, these are chiral centers now. So this carbon and this carbon down there are chiral centers, and so they each will come in 2 versions, a right-hand version and a left-hand version, and there's no preference for which version you have, so you'll actually get a mixture. So in the answer you'll see that you not only get this one, but you also get the enantiomer. And the enantiomer is what you'd get if you drew that same molecule, but just with the opposite handedness on each of those carbons. So the top one's coming out at you instead of going away, and the bottom one's going away instead of coming out at you. So that's what the enantiomer is. All of the chiral centers switch. So these two would be your answer for that Diels-Alder reaction. And notice that the En and the bottom one, those are just the same thing. So in this one, it might seem a little strange at first. We have a triple bond, but you'll see that the procedure for predicting the product is really going to be the same. The first thing I would do is to line them up so that you can sort of draw those dotted lines like we've been doing. So let's do that. You've got that diene, and then here I'm going to have that triple bond in a place that is going to make it easier for me to see the reaction. Now on either side I have an electron withdrawing group. So I've just taken this molecule and rotated it counterclockwise. Okay, so now we can follow our procedure, draw a dot at the end of the conjugated system of the diene, and dots at the end of that pi bond in the dienophile, and draw dotted lines between those two. Now, I'm going to draw in the pi electrons that are going to move in different colors, so we can keep track of them. And those pi electrons all move those all in the same direction. So here I'm going to move them all clockwise, one bond over. And if it helps you to keep track of things, sometimes it's useful to number the carbons in this chain. So we'll draw in that carbon skeleton for the diene, and then the carbon skeleton for the dienophile. And let's number those, and then we'll think about everything that's attached here. Okay. The purple electrons are going to go from being between carbons 1 and 2 to being between carbons 1 and 6, so those form that sigma bond there. The green electrons will go from being between carbons 5 and 6 to being between carbons 4 and 5, so you'll get that new sigma bond there. And the blue electrons will go from being between carbon 3 and 4 to being between carbons 2 and 3. So you'll get that new pi bond there. So we've taken into account those colored electrons. Notice that in the original structure, though, we still have another pi bond between carbons 5 and 6, and so that pi bond will still be there. Now we just need to put the electron withdrawing groups in. And notice that because you have a double bond here now, those two carbons at the end of that chain on 5 and 6, those two carbons are sp2 hybridized. So they're flat. The electron withdrawing group isn't going to come out at you, it's not going to go away. It's a flat molecule, sp2 hybridized, and so it's going to be in the plane. And so you draw those electron withdrawing groups in the plane there. And that would be the product you'd get for that. That would be the product of that Diels-Alder reaction. With E, the procedure is similar, and they're being nice to you. They're lining everything up neatly. So draw dots at the end of the conjugated pi system of the diene, dots at the end of the double bond in the dienophile, and then draw dotted lines between those two. I'm going to draw in colors here for the pi electrons so we can track how they're moving a little more easily. And then pick a direction. I like to go clockwise myself, but you could go counterclockwise, and just make sure you move all of those pi electrons one bond over in that direction. They all have to be going in the same direction. If it helps you, you can number the carbons in the diene and the dienophile to help you keep track of stuff. So here we will have the carbon skeleton for the diene, the carbon skeleton for the dienophile. Just to help us keep track of where everything should be, I'm going to put those numbers in. So these green pi electrons are going to go, or actually let me start with the purple ones. The purple pi electrons are going to go from being between carbon 1 and 2 to being between carbon 1 and 6. So those form that sigma bond there. The green electrons are going to go from being between carbons 5 and 6 to being between carbons 4 and 5. So they're going to form the second sigma bond here. And the blue electrons are going to go from being between carbons 3 and 4 to being between carbons 2 and 3. So they're going to form that new pi bond there. So those are the way the electrons move, and now we just need to think about adding in those electron withdrawing groups. Now, if you notice in that original molecule, if you were to draw a dotted line down the long end of the double bond, you'll see that the two groups coming off of that are on the same side of that dotted line. They're both to the right of it. And so those are cis. And so we're going to want those two going in the same direction. So we can either have them both coming out, oops, or both going away. Either way, it's the same. And so then we'll just have that oxygen there, the double bond there, and that would be your product for this Diels-Alder reaction. And an equivalent product, the same exact molecule, just viewed from a different direction, would have these two bonds as dashed wedges. Okay, so then F. So I'm going to actually, we've gone through these, there's a lot of these practice problems, we've gone through them really meticulously so far, so let's try to do them a little bit faster, see if we can do that. So I'm just going to draw them first, how they are, but I'm going to draw them so that they line up nicely. And I'm going to draw that dotted line between the ends. I'm going to draw those electrons moving over. And so we're going to have that six-membered ring. But now we have a pi bond on this left side. We moved one pi bond over, but we're going to have another pi bond left on this right side. So these are sp2 hybridized carbons. So the electron withdrawing groups there are going to be in the plane rather than coming out or going away. So that would be the product for that Diels-Alder reaction. I think I'm going to do the rest of these. I'll go the slower way, but I'm going to do those as a different video because I don't want the video to get unduly long.